let's Boltzmann Q A. What is the difference between Taylor expanded and moment-matched equilibrium? So this is a very interesting question that I believe many so-called specialists in lattice Boltzmann could not actually answer. So first, let us remind the practical difference between the two methods to compute an equilibrium. The first one is a Taylor expanded equilibrium. This is usually Taylor expanded to second order. So we have velocity terms up to second order in the equilibrium equation. We have an Wij as the lattice weights. We have these lattice velocities, and what you see down here is that the equilibrium function is a function of these monomials in velocity. So the first one, ux by the power of 0, uy by the power of 0, this is of course 1. Then the next one is ux, uy, uxy, ux square, and uy square. So these are all the zero order, first order, and second order terms in velocity that appear here, and then we cut the Taylor expansion off. Okay, and this equilibrium is independent from the lattice that we are using. So for any lattice that you could think about, we would use the same equilibrium function. Of course, this lattice has to be large enough, so it has to have enough speeds to actually cover all these velocities. So, however, as you see, we have 9 speeds, and we have only 1, 2, 3, 4, 5, 6 different velocity monomials. So actually, what we can do is we can, when we use moment matching, we can use one monomial for each moment that we add. So what we do in moment matching is saying that the moments of the lattice Boltzmann method that we are taking in equilibrium should be the same as the Maxwell-Boltzmann equilibrium. And the moments are of course defined as a monomial in velocity multiplied with f, and this summed over all the velocity directions. So for each moment that we have, for each independent moment that we have on our lattice, we can add another monomial. So this means now in the D2Q9 lattice, we would have 9 monomials, and in the D3Q27, we would have 27 monomials. So these are obviously more monomials than we would have with the Taylor expansion. Okay, so but both of them solve the Navier-Stokes equation, so it's fair to ask what is the difference. So of course the lattice Boltzmann method is an approximative method, and it solves the Navier-Stokes equation only up to an error term, and this error term is an error in the velocity, and this is usually a third order in velocity term. And the way this third order error in velocity looks like is different between the Taylor expanded and the moment matched method. So in the Taylor expanded method, the good thing is we have an isotropic error, that comes as this square of velocity together with the viscous term, and is added in this way to the Navier-Stokes equation, where we have this velocity square term in front of the viscous term. So we get a velocity dependent viscosity. So we also get a velocity dependent viscosity with the moment matched method. However, here it looks a little bit different because we get this error only in particular directions. So these terms also exist in the Taylor expanded version, but there are parts that exist in the Taylor expanded version which do not exist in the moment matched version. And now, of course, one question is, when we do this moment matching, why don't we correct all the errors? The problem that we have, if we are on a lattice like the D2Q9 lattice, is that we have actually missing moments, like the moment M30 is missing and the moment M03 is missing. And this implies that also the velocity monomials ux cube and uy cube are also missing. And they would be required to repair all the error terms. So we repaired some error terms, but we could not repair all the error terms. So if we cannot repair all the error terms, what is still the practical consequence? Well, as I just said, the consequence of this cutting off the velocity after the second order gives us a velocity dependent viscosity. So this matters, for example, if we have a vortex like the one indicated here, and this vortex moves in a velocity field with a velocity u, then the decay of this vortex is dependent on the velocity. So, for example, if the exact decay of the amplitude over time is the black line here, then the moment matched equilibrium, so the vortex simulated with the moment matched equilibrium, will decay slightly slower, and the size of this error is larger for the Taylor expanded equilibrium. It's almost nearly twice as large. So you can actually cut the error in half by using the moment matched equilibrium, but you cannot eliminate the error in this way. So the reason, as I said, was, of course, that there are these missing moments, and fortunately the same problem can be solved in a different way, but this is now a little bit more advanced and is not covered also in our lecture to this extent. So what we can do, and I only give you a rough overview, is that you can modify the equilibrium of the second order moments by adding some terms like these that are related to the viscosity and the velocity square and the gradient in velocity. So if we add this to the equilibrium, we can compensate for the non-existence of these third order moments, and by so doing we can actually correct the viscosity completely to second order in velocity, such that we would not have anymore this velocity dependent viscosity. Okay, but this requires the knowledge of the velocity gradient, and fortunately the velocity gradient can be computed locally from the second moment itself. So this is a little bit strange, because in order to correct the second order moment, we have to know the second order moment. And well, this is done by asymptotic analysis, which we learn in lecture 6. So through to asymptotic analysis, we can compute the gradient of the velocity from the non-equilibrium moments of second order. And here it is actually sufficient to use the usual equilibrium without the add-on, because the add-on is only a very small modification thereof. Yeah, it is an error that we would otherwise accept. So we get a sufficiently good approximation of the gradient of the velocity here by just using the equilibrium without adding the term for the compensation of the missing third order moment. So that would be sufficient. Okay, conclusion. The moment-matched equilibrium is usually more accurate and also more stable than the Taylor-expanded equilibrium. So you should actually use this one if you have the choice. There is in the moment-matched equilibrium still an error in viscosity, and this can be repaired by this modified equilibrium, which of course is an advanced topic. And even if you do this, unfortunately, still some errors in the methods will remain. So that's all for this brief update. Thank you for listening.